Tonight, you're not just going to sleep, you're going to drift off on a planet-sized ocean. As you lie back and close your eyes, we'll quietly walk through some of the strangest, calmest, and most mind-bending facts about the sea, from the crushing stillness of the deep to glowing animals drifting in the dark, all explained in simple, gentle language. No jump scares, no loud drama, just a slow, steady stream of, wait, I didn't know that, moments about the water world you actually live on, easing your brain away from the day and into the kind of deep, quiet space where sleep comes naturally. But before we continue, please subscribe to the channel to give your support. Let's continue. Do you realize you live on a planet where water is in charge and land is just what happens when the water gets shallow enough for you to stand? From orbit, Earth is not a green planet or a brown planet, it is a blue one. And that is not a branding choice, that is a measurement. About 71% of Earth's surface is covered by ocean, almost 3/4. So most of the solid crust under your feet is actually underwater, not under cities, not under forests. The continents you know so well are the small, exposed parts of a much larger rocky shell that is mostly hidden below sea level. The numbers behind that are blunt, not poetic. Earth's oceans hold around 1.335 billion cubic kilometers of water. That is roughly 320 million cubic miles. In normal daily life, you almost never use numbers that large because you never have to think at planetary scale. But on the scale of a whole world, that is what matters. If you split that ocean water evenly across the planet, you would have a continuous layer of water several kilometers deep, everywhere, wrapping the whole globe. That is the kind of world you actually live on, and yet you spend almost all your time thinking about the minority part, the land. This raises a simple question. If most of the surface is ocean, is it at least shallow? Is it just a big, wide swimming pool? The answer is no. The average depth of the ocean is around 3,700 meters. That is about 12,100 feet. For comparison, most commercial airplanes cruise at around 10 to 12 kilometers above the ground. So if you could flip that, the typical ocean is like putting a smaller but still serious cruising altitude worth of water above your head. That is the normal baseline of this planet, thousands of meters of water over most of the crust. Think about the ocean floor in another way, not as a flat bottom under a beach, but as the main surface of the planet, completely out of your sight. If you could remove the water without changing anything else, you would reveal a world with giant valleys, long mountain chains, and deep trenches, many of them far more dramatic than anything you see on land. Mount Everest reaches about 8,849 meters above sea level, which sounds enormous until you notice that the deepest ocean trenches go down almost the same distance below sea level, and the average seafloor still sits several kilometers down. In other words, normal, everyday Earth is not a calm, flat seafloor with a bit of water. It is a rugged planet buried under a very thick liquid layer. Here's the next twist. The part of the ocean you know, the bright blue sunlit layer near the surface, is the exception, not the rule. Ocean scientists draw an important line at about 200 meters depth, around 660 feet. Above that, there is still enough light for photosynthesis. There's plenty of mixing from wind and waves. This is where most familiar marine life and human activity happen. Below that line, you are in what is broadly called the deep ocean, and that deep zone, everything below 200 meters, covers roughly 66% of Earth's surface. 2/3 of your planet's surface is permanently in a realm where sunlight is weak or gone, pressure is high, and temperatures are cold. So the map in your head, with continents, coastlines, and a blue background that you treat as water, is badly biased. You live on land, so you treat land as the default. But if you stepped back and looked at Earth like a scientist from another solar system, you would not call this a land planet at all. You would classify it as an ocean planet, because the dominant environment, by area and by volume, is deep water. The familiar surface world, cities, roads, farmland, mountains, is a thin, patchy boundary zone along the top edge of a much larger system. And that system is not shallow even at its ordinary depths. Over half of the seafloor lies between about 4,001 and 6,000 meters depth. That is 4 to 6 kilometers, or roughly 13,000 to 20,000 feet under the sea surface. Picture your favorite big mountain range on land, then put the whole thing under 4 to 6 kilometers of water and stretch that kind of depth out over an area larger than all the continents combined. That abyssal depth range, those 4 to 6 kilometers, is not a rare extreme. It is the main category of seafloor on this planet. There's a quiet but important consequence here. In daily life, you think in 2 dimensions, maps on a flat screen, coastlines, but the ocean forces you to think in 3 dimensions. The bulk of the planet's habitable volume, the actual space where liquid water exists, is not on the surface. It is in this stacked, vertical column of ocean. That changes how heat moves, how chemicals cycle, and how life evolves. Land ecosystems cover a small fraction of Earth's total surface and volume. The ocean holds most of the water, most of the transport of heat, and a large share of the total biomass. You might ask, how big is this water volume compared to the size of the planet itself? Is it just a thin film or something more serious? If you spread all 1.335 billion cubic kilometers of water evenly across Earth, each square meter of surface would have on average a water column about 2.6 kilometers thick sitting on it, which is around 1.6 miles. That is the average load the solid Earth is carrying in terms of ocean weight. So in a very direct, physical sense, you live at the bottom of a global ocean system, under a moving, flowing mass of water that wraps around the crust on all sides. This is the key mental shift. Instead of picturing yourself standing on top of a solid planet with some water on it, you should picture yourself living at the interface between rock and ocean, inside a fluid-dominated system. The ocean is not a side feature. It is the main environment, the main reservoir of water, heat, and chemicals dissolved. The atmosphere you breathe, the climate patterns you depend on, and even the long-term stability of ice sheets and coastlines are all controlled first by what the ocean does, and only second by what happens on land. So here's the next uncomfortable question that follows from that. If water really owns most of the planet by area and by volume, and if most of that water sits in deep, dark, high-pressure zones you never directly experience, how extreme are the conditions down there and what kinds of forces are quietly shaping your future from thousands of meters below the surface? You think the harshest place you could go is outer space, but the deep ocean on your own planet would crush a spaceship before it reached the bottom, and it does that every second of every day. Up here at the surface, you live under 1 atmosphere of pressure. That is the weight of all the air stacked above your head. As soon as you go underwater, you add the weight of water on top of that air, and water is much heavier than air. The rule of thumb is simple. For every 10 meters you go down, about every 33 feet, the pressure goes up by roughly 1 extra atmosphere. At 10 meters depth, you feel about 2 atmospheres. At 20 meters, about 3, and it keeps climbing. Now scale that up for real ocean depths. The average seafloor is not at 50 meters or 100 meters, it sits around 3,800 meters down, about 12,500 feet. For comparison, most commercial airplanes cruise at around 10 to 12 kilometers above the ground. So if you could flip that, the typical ocean is like putting a smaller but still serious cruising altitude worth of water above your head. That is the normal baseline of this planet, thousands of meters of water over most of the crust. If the average depths already sound extreme, the deepest trenches go much further. Down in the Mariana Trench at the Challenger Deep, you're looking at roughly 11,000 meters of water above you, around 36,000 feet. Using the same rule, 1 extra atmosphere every 10 meters, that puts you at well over 1,000 atmospheres at the bottom. That is more than a metric ton pressing on every square centimeter, or roughly 8 tons on every square inch. On the scale of your thumbnail, the force on that tiny area would be comparable to parking a stack of heavy trucks on it. This is not a minor design issue. This is a different regime. Electronics, batteries, seals, windows, everything behaves differently when every component is squeezed from all sides by that much force. That is why many deep ocean probes are either filled with incompressible fluids or built with pressure-tolerant electronics that do not rely on a big, hollow, air-filled hull. In a direct sense, the deep ocean is not a place for you. It is a place where physics has reset your idea of what counts as extreme. You might think there is at least some visual payoff for reaching those depths, but light does not cooperate either. Sunlight only penetrates clearly through the upper few hundred meters of seawater. By the time you get down to around 1,000 meters, roughly 3,300 feet, sunlight is basically gone. Below that, you enter what scientists call the midnight zone. Photosynthesis stops because there is no usable light left. Plants and algae cannot make food from sunlight anymore. Life down there runs on different energy sources: falling organic particles from above, chemical reactions around vents and seeps, or simply eating anything that swims or sinks within reach. So as you go deeper, pressure goes up, light goes down, and your normal senses become almost useless. Vision is limited to whatever artificial lights you bring or the faint glows of bioluminescent organisms. Sound and chemical detection become more important. From a human point of view, this is a hostile sensory environment. But for the species that evolved there, this is home. Their eyes, if they have them, are tuned for darkness, or they rely on long feelers, pressure sensors, and chemical cues instead of sight. Then comes the temperature problem. Typical deep-sea temperatures hover around 2 to 4 degrees Celsius, around 35 to 39 degrees Fahrenheit. That is just above the freezing point of seawater. Under those conditions, heat moves out of your body very quickly, and many of the chemical reactions that run your metabolism slow down. But the water does not actually freeze because the salt content and the pressure push the freezing point down slightly. So you end up with a liquid environment that is near freezing but almost never turns to ice. This combination, almost no light, very high pressure, and near freezing temperatures, sounds like a dead zone. Yet, the deep ocean is full of life. Deep-sea organisms are not just regular fish that got used to it. They're built from the ground up for those conditions. Their proteins and cell membranes are packed with special molecules that keep them flexible and functional under hundreds, even over 1,000 atmospheres of pressure. Their bodies often lack gas-filled spaces like swim bladders, which would collapse, and instead they use fats, oils, and gels to control buoyancy. On top of that, their metabolisms are slow and efficient. Many deep-sea fish and invertebrates grow slowly and can go long periods without food. They match their whole lifestyle to an environment where energy is scarce and conditions are stable for thousands of years. If you bring these animals up to the surface too quickly, the same way a diver can get the bends, their internal chemistry can fail and their tissues can be damaged. They can die, not because the surface is harsh by your standards, but because it is harsh by theirs. So now you have a planet where most of the habitable volume is under crushing pressure, in permanent night, and near freezing temperatures, and yet that volume is not empty. It is alive and active. The everyday surface world you know is mild and temporary compared to that. Which leads to the next question. If the deep ocean is already this extreme and this full of adaptations you barely understand, how much stranger is it that you have mapped distant planets like Mars in more detail than the seafloor on your own world? And what exactly are you missing under those kilometers of water? How is it possible that you have sharper maps of dry, airless rocks millions of kilometers away than of the seafloor under your own feet on the same planet? When people say we've mapped the ocean, they usually mean we have some rough idea of depth over large areas, not that we have detailed high-resolution maps like you see for cities and mountain ranges on land. If you look at the numbers, as of recent estimates, only about a quarter of the global seafloor, around 27 to 27%, has been mapped with modern high-resolution sonar. That means roughly 3/4 of the seafloor is still in low detail mode. Meanwhile, Mars and even Venus have nearly complete global maps at comparable or better resolution, thanks to orbiters with radar and cameras that can scan entire planets from above, across millions of kilometers or millions of miles of space. So there is a real mismatch here. You walk around acting like Earth is the familiar one, the known one, while your data actually treats Earth more like a half-finished survey project. You have contour lines, you have depth estimates, but for most of the seafloor, you do not have the kind of detailed view that would let you talk confidently about every small ridge, every canyon, every landslide scar. A lot of what you think you know about the deep ocean floor is still shaped by interpolation, by filling in gaps between sparse measurements. This is why it matters how you use the word mapped. For the ocean, there are two very different levels. At the coarse level, you can use satellites to measure tiny changes in sea surface height. Those changes are caused by gravity variations from underwater mountains and trenches, and from that you can infer rough shapes of the seafloor. That gives you a broad, low-resolution picture, enough to say there is probably a ridge here, a basin there. But when scientists talk about mapped with modern high-resolution sonar, they mean something else. They mean multi-beam sonar data that can resolve fine details, the way a good topographic map on land can show you individual valleys and peaks. High-resolution mapping means sending ships back and forth in tight, overlapping lines, with sonar beams sweeping the seafloor and recording precise depths. It's slow, it's expensive, and it only covers a limited swath on each pass. You go from "we kind of know there's a bump here" to "we can see the exact slope and structure of this seamount." That's the level you need if you care about submarine landslide hazards, detailed habitat mapping, or planning cables and pipelines. And right now, 3/4 of the ocean floor is still waiting for that treatment. The next question is, how much of the seafloor have you actually seen directly, not just measured with sound? The answer is almost none. One recent analysis suggests that about 0.001% of the deep sea floor has been visually observed through cameras on submersibles or towed vehicles. That's an area smaller than the US state of Rhode Island, only a few thousand square kilometers, a bit over 1,000 square miles. To put that in simple terms, it's like trying to understand an entire megacity by walking through a single building, and then guessing everything else from that one sample. Most of the planet's deep terrain has never been in front of a camera. This is why deep-sea science still produces genuine surprises. You send the camera into a trench or along a mid-ocean ridge, and you don't just confirm what you expected, you often find entire communities of life or unexpected mineral formations that were not in your model. You're still at the stage where basic exploration, just going there and looking, changes textbooks. So why is it taking so long? If mapping space is easier than mapping your own planet, what's slowing you down under the water? The fundamental problem is that your usual tools don't work. Light doesn't penetrate far, so you can't rely on normal cameras or optical satellites. GPS signals don't go through seawater, so anything under the surface cannot simply check its position against satellites. Sound does travel, but it does so in a complicated way, bending with changes in temperature, salinity, and pressure, so sonar data always needs careful correction. Every strip of high-resolution data you have is the result of a physical ship or an autonomous vehicle slowly moving over the area, sending out sound pulses, recording echoes, and then processing that data. There is no cheap, fast shortcut that lets you cover everything in one go. On top of that, the ocean is huge and ships are slow. Even if you had a fleet of dedicated mapping vessels, they still have to cross rough seas, avoid bad weather, and refuel. Underwater drones help, but they also need support ships and careful planning. Because of that, mapping the ocean became a global project instead of a single mission. The Seabed 2030 initiative is the main push to fix this. Around 2017, only about 6% of the seafloor had been mapped at modern, high-resolution standards. By 2024, that had jumped to roughly 26%, thanks to new surveys, better data sharing, and reprocessing of older datasets. The goal is straightforward but ambitious. Pull together a complete high-resolution map of 100% of the seafloor by the year 2030, using contributions from governments, research ships, industry, and even private vessels. If that goal is met, your generation will be the first in human history to actually see a full map of its own planet's surface, including the 3/4 that sit under the ocean. That is more than a nice graphic for a textbook. It changes how you handle everything from undersea cables and shipping routes to tsunami modeling, resource management, and conservation. You cannot protect, use, or even properly understand a terrain you have never seen in detail. But there is a tension running through this, because better maps will not just show you smooth plains, they'll reveal the true scale of underwater mountain chains, deep trenches, and massive submarine canyons that make your biggest land features look small. So the real question now is, when you finally cut through that ignorance and see the full shape of the seafloor, how will your idea of Earth change again? When you realize the planet's largest mountain ranges and deepest canyons have always been hidden under kilometers of water. You've been trained to think the big action on Earth happens on land. Giant mountain ranges, deep river canyons, dramatic cliffs, all of that. But the largest structures on this planet are not on any continent you've ever stood on. They are hidden under kilometers of water, and they run almost completely out of your direct experience. Start with this. The single longest mountain chain on Earth is not the Himalayas. It is the mid-ocean ridge system, and you never see it with your own eyes unless you send a robot down. This ridge is more than 60,000 kilometers long, around 37,000 miles. It wraps around the planet in one continuous system, like a seam on a baseball but stretched around the sphere the size of Earth. Along this ridge, tectonic plates are pulling apart. Magma from the mantle rises up, cools, and forms new oceanic crust. That means the seafloor under you is not just sitting there static. It is being manufactured and pushed sideways all the time, just very slowly, usually a few centimeters a year, an inch or two. If you could see through the water the way satellites see land, you would see this huge broken scar running through every major ocean basin, with peaks, valleys, fracture zones, and volcanic vents. The mountain relief is real, thousands of meters from valley floor to ridge crest. But water hides almost all of it, so in your mind, it barely exists. Now look at the other extreme, the places where the seafloor bends down and dives back into the mantle, the ocean trenches. The deepest one we know on Earth is the Mariana Trench in the Western Pacific. Inside that is a spot called Challenger Deep, where the depth reaches around 11,900 to 11,000 meters, about 36,000 feet below sea level. Mount Everest, the highest mountain on land, is about 8,849 meters, roughly 29,000 feet high. So if you put Everest into the Mariana Trench, base at the bottom, you would still have more than a kilometer of water over its summit. These trenches are not cracks. They are vast, long, steep-sided depressions where one plate is sliding under another. These extreme depths are not rare, isolated holes. They're part of long trench systems that can stretch for thousands of kilometers along plate boundaries. The pressure, darkness, and low temperature there are already extreme, but the geology adds another layer of violence. Earthquakes, slow grinding motion, and occasional huge landslides along the trench walls. In a direct way, these deep structures are where the planet recycles its crust, pulls old seafloor down, and drives some of the largest earthquakes and tsunamis that ever hit coastlines. If you think that's big, look at the coldest, most remote part of the ocean system, around Antarctica. Recent high-resolution mapping has revealed 332 massive submarine canyon networks carved into the continental margin around the Antarctic continent. Some of these canyons are more than 4,000 meters deep, about 13,000 feet, from the shelf down into the deep basin. They're like underwater highways for water, ice, and sediment. Dense, cold water formed near the icy surface spills down these canyons into the deep ocean, dragging sediments with it. These Antarctic canyons aren't just interesting shapes, they're part of the control system for the planet's ice sheets and ocean circulation. When dense, cold, salty water sinks through them, it helps set up deep currents that circle the globe. The shape and depth of those canyons influence how quickly heat can move in and out under ice shelves, which affects how stable or unstable those ice shelves are. That means an underwater canyon you will never see can influence how fast coastal cities thousands of kilometers away will have to deal with sea level rise. The geometry of the seafloor turns into a long-term risk factor for human infrastructure. Now, connect this back to volcanic activity. When you think of volcanoes, you might picture big cones like Mount Fuji or Mount St. Helens. But most volcanic activity on Earth is not happening there. It's happening underwater along mid-ocean ridges. As plates separate, magma wells up, cools in contact with seawater, and builds new crust. There are also underwater volcanoes called seamounts, some of them active, some extinct, rising thousands of meters off the seafloor, many never breaking the surface. This underwater factory of new crust is running all the time, releasing heat and chemicals into the ocean. Hydrothermal vents on the ridge flanks pump out hot, mineral-rich fluids. This does more than alter local chemistry. It sets up gradients that life uses as an energy source, and that influences how much heat from inside the planet is leaked into the ocean. On a geological timescale, this steady output shapes the thickness and density of oceanic plates, which controls how they float, how they bend, and where they eventually dive back down into trenches. So at this point, it should be clear these ridges, trenches, and canyons are not background scenery. They are the main structural elements of the planet, and they directly affect the ocean that sits on top of them. The shape of the seafloor determines where deep currents can flow, where they are blocked, and where they have to squeeze through narrow passages. Those bottlenecks create fast jets, slow pools, and mixing zones where cold, deep water meets warmer surface water. In other words, the deep landscape directs the plumbing of the global ocean. That plumbing is what carries heat around the planet. Take something like the global thermohaline circulation, the so-called conveyor belt of deep and surface currents. It depends on where water can sink, where it can slide along the bottom, and where it can rise back up. Underwater ridges can steer or block these flows, forcing water to go around them, changing how long it takes for deep water to complete a circuit. Submarine canyons and slopes can generate internal waves and turbulence that mix layers vertically, moving heat and nutrients up and down. On even shorter timescales, the roughness of the seafloor controls where eddies form, where nutrient-rich deep water is brought closer to the surface, and where oxygen-poor water can get trapped. That sets up hotspots for marine life, major fishing grounds, and also dead zones where little can survive. So when you look at a weather map or a climate model projection, you're indirectly looking at the result of water being forced to move over a jagged, three-dimensional underwater landscape you rarely think about. This is the key point. Deep geology is not separate from the climate system. It is one of the main boundary conditions that climate runs on. The mountains and canyons you never see help decide where water can store heat, how fast it can release that heat, and where carbon-rich deep waters can be brought back into contact with the atmosphere. They shape the pace of natural climate swings, and they set some of the limits on how the ocean can respond to human warming. So now the tension ramps up, because once you accept that hidden mountain ranges and canyons under the ocean are quietly steering your currents and your climate, you have to ask a harder question. If the ocean is riding over this extreme terrain, constantly taking in heat and carbon from the atmosphere, how much of your future is already locked into the way this giant, slow-moving system responds? And how long will it take before changes in the deep ocean show up in the air you breathe and the weather you live through? You hear about climate change as if it's happening in the air above your head. But the real action, the main storage, and the long-term consequences are in the ocean that surrounds you. The ocean is not just a backdrop that gets a bit warmer. It is the main engine and the main battery of the whole climate system, and that is already running on a different setting than it used to. Start with heat. Greenhouse gases trap extra energy from the sun. That extra energy has to go somewhere, and over 90% of it ends up in the ocean, not in the air, not in the soil, in the water. That means when you see graphs of air temperature rising by 1 or 2 degrees Celsius, you are only seeing the tiny leftover piece that did not get swallowed by the sea. Water has a high heat capacity, which means it takes a lot of energy to raise its temperature by even 1 degree. So when scientists say the average ocean temperature has climbed by around 1 degree Celsius, or about 1.8 degrees Fahrenheit, that is not a small change. It is a signal that the ocean has soaked up an enormous amount of extra energy, equivalent to millions of Hiroshima-scale explosions spread out over decades. You don't see that as fire and blasts. You see it as slightly warmer water, more frequent marine heat waves, bleaching on coral reefs, and shifting fish populations. But in terms of physics, that hidden energy is real, and it is stored in a system that reacts slowly. Even if you froze emissions today, the ocean would keep redistributing that heat for decades to centuries, moving it around the globe, bringing it back to the surface in some places, hiding it in the deep in others. The ocean is like a slow-moving flywheel. Once you've put extra energy into it, you do not stop it quickly. So the question is, how does this water move that heat around? What is the mechanism that quietly connects a meltwater pulse in Greenland to rainfall patterns in the tropics and to temperature shifts thousands of kilometers away? This is where the thermohaling circulation comes in, the so-called global conveyor belt. At high latitudes, especially in the North Atlantic and around Antarctica, seawater gets very cold, and in some regions it also becomes very salty as sea ice forms and leaves salt behind. Cold, salty water is dense, so it sinks down hundreds, then thousands of meters, sliding along the seafloor and spreading out as deep currents. That dense water slowly creeps across ocean basins, mixes, and eventually, in other regions, rises back toward the surface, where it warms and flows back as surface currents. The whole loop, from sinking to resurfacing and back again, takes on the order of 1,000 years to complete a full circuit. So this is not weather. This is deep climate infrastructure. But it is absolutely central to how heat and nutrients are distributed on Earth. When surface water sinks, it carries oxygen from the atmosphere down with it. When deep water rises, it brings nutrients from decomposed organic matter back up to the sunlit zone where plankton can use them. Areas where this upwelling happens strongly often become major fisheries because the entire food web gets a boost. If you weaken or reroute parts of this conveyor, you do not just move some water. You change how whole regions get their heat and nutrients. So the next concern is obvious. If the ocean is taking in extra heat and extra fresh water from melting ice, how long does it stay in its current pattern? And what happens to your climate if that slow conveyor belt shifts even a little? Heat is not the only thing the ocean is absorbing. It is also taking in part of the carbon dioxide you release. Roughly a quarter of human CO2 emissions so far have gone into the ocean. At first glance, that sounds like the ocean is doing you a favor, slowing the buildup of CO2 in the atmosphere and delaying the worst warming. But CO2 in seawater does not just disappear, it reacts. When CO2 dissolves, some of it forms carbonic acid, which then shifts the balance of carbonate and bicarbonate ions in the water, nudging the pH downward. The change in pH is only a few tenths of a unit on the standard scale, but that scale is logarithmic, so a small numerical shift represents a big change in acidity. This is why scientists call the ocean a CO2 sponge with limits. It can keep taking up carbon for a while, but the chemistry of that dissolved carbon slowly makes the water more corrosive to certain minerals, and it changes the conditions for marine life that evolved under a more stable pH. In simple terms, the ocean is buffering your emissions, but it is paying with its chemistry. So you have to ask, if the ocean is protecting you in the short term by absorbing CO2 and heat, what bill is that sending to marine ecosystems, and how does that come back to you later through food, jobs, and coastal protection? You can already see part of that answer in the way acidity affects shell-building organisms. Since pre-industrial times, average ocean acidity has increased by roughly 30%. Another way to say it is the pH has dropped slightly, but enough that calcium carbonate, the main material in shells and coral skeletons, is harder to form and easier to dissolve in many regions. Corals, clams, oysters, some plankton species all rely on having the right balance of carbonate ions in the water to build and maintain their structures. When the water becomes more acidic, young shellfish can struggle to form their first shell. Coral reefs can grow more slowly or even start to erode if breakdown outpaces growth. Reefs aren't just pretty tourist sites. They are three-dimensional habitats that shelter fish, protect coastlines by breaking waves, and support local economies. As acidity goes up and temperature stress increases, mass bleaching events and reef die-offs become more common. That feeds back into fisheries, tourism, and natural storm protection. This is not just a problem for tropical reefs. Cold, high-latitude waters absorb CO2 more quickly, so some of the earliest and strongest acidification impacts show up in polar and subpolar regions, where important fisheries live. Pteropods, tiny shelled plankton often called sea butterflies, are a food source for many larger animals, and their shells become more vulnerable as conditions change. Step by step, acidification works its way up the food web. So now you have a system where the ocean is warmer, holding more CO2, and changing in chemistry. The logical next question is, how does this altered ocean send signals back to the atmosphere you live in through the pattern of currents that set up your day-to-day weather? Major currents are the delivery routes for ocean heat. The Gulf Stream in the North Atlantic, for example, moves warm surface water from lower latitudes toward Europe. That flow helps keep Western Europe much milder in winter than other regions at similar latitudes, like parts of Canada. The Antarctic Circumpolar Current, a powerful band of water that circles Antarctica, connects the Atlantic, Pacific, and Indian Oceans, helping to redistribute heat and carbon between them. These are not details, they are structural features of the climate system. But when these currents change speed, position, or structure, storm tracks can shift, jet streams can be nudged north or south, and patterns like monsoons can be strengthened or weakened. For billions of people, that means changes in when and how much it rains, how often heat waves hit, how intense hurricanes or typhoons can become, and how long droughts last. Even modest changes in upper ocean temperature in key regions can load the dice toward more extreme events, because warm water feeds evaporation and powers storm systems. You see this clearly in phenomena like El Niño and La Niña, which are driven by shifts in winds and current in the tropical Pacific. When warm water piles up in the eastern Pacific, global weather patterns respond, bringing floods to some places and droughts to others. Now layer on top of that a general trend of a warmer, more stratified ocean with altered currents, and the background conditions for these events start to change too. This is the uncomfortable bottom line. The ocean is not just passively warming, it is reorganizing heat, carbon, and nutrients on timescales from years to centuries, and that reorganization decides a lot about the climate you actually feel. And yet, this is all happening out of sight, below the surface, communicated not by light, but by something else entirely, which raises the next question. In a world where light barely reaches beyond a few hundred meters, what really carries information and stress through this vast water column? And how much of the story are you missing because you are not listening to the sounds that rule the deep? How do you send the message in a world where light barely works, but you still need to find food, mates, and predators before they find you? In the deep ocean, the main communication system is not light at all, it is sound. And the physics of water turns the entire ocean into a kind of acoustic network that runs around the whole planet. Start with speed. In air near sea level, sound moves at around 340 meters per second, about 1,125 feet per second. In seawater, that jumps to roughly 1,500 meters per second, around 4,900 feet per second, more than 4 times faster. The reason is straightforward. Water is denser and more elastic than air, so pressure waves move through it more efficiently. For you, that means any noise in the ocean, from a snapping shrimp to a submarine engine, propagates fast and far. So in a medium where light fades out within a few hundred meters, sound becomes the practical way to sense the environment at a distance. Marine animals use it to navigate, to hunt, to avoid predators, and to stay in contact. Humans copy that, using sonar to map the seafloor and to detect objects underwater. Once you realize sound can travel so far in water, you start to see the ocean as a continuous acoustic field, where everything loud enough influences everything else in a large radius. That leads to a key question. If sound spreads so well, is there any way for it to travel truly long distances without losing strength? Or does it just fade out like any other wave? There is a special trick the ocean plays here, called the SOFR channel, short for sound fixing and ranging. At a certain depth, typically a few hundred to about 1,000 meters, depending on location, temperature, and pressure, combine in such a way that the speed of sound reaches a minimum. Above this layer, the water's warmer and sound is a bit faster. Below it, pressure is higher, and again, sound is a bit faster. That minimum acts like a kind of trap, bending sound waves back toward the center of the layer. The result is, if a sound source sits near that depth, its energy gets guided along the channel instead of just spreading outward in all directions and fading quickly. Signals can travel thousands of kilometers, thousands of miles, with much less loss than they would near the surface. The ocean essentially provides a natural long-distance phone line. Large whales, especially species like blue whales, take advantage of this. Their low-frequency calls can slide into the SOFR channel and propagate across entire ocean basins. A single call can be detectable hundreds, even thousands of kilometers away by sensitive instruments. For the whales, that means individuals separated by vast distances can still exchange information, coordinate, or at least become aware of each other. So now the next question is obvious. If whales can use this channel to speak across basins, how far does the reach of a single animal really extend? And what happens when you start flooding that same channel with artificial noise? Blue whales, fin whales, and some other large species produce very low-frequency sounds, often below the range of easy human hearing. These long wavelength signals are perfect for long-distance travel, because they scatter and absorb less than higher frequencies. You can think of high-pitched sounds as detailed but short range, and low-pitched sounds as simple but long range. In the ocean, the long-range option is the one that matters most when you need to connect over huge distances. For a blue whale, that means it can potentially advertise its presence over an entire ocean basin. Individuals that may never see each other directly can still be linked through sound. For mating, for maintaining loose population structure, and possibly even for navigating large-scale features of the ocean, this acoustic communication is central. It is not just whale songs as background noise, it is core infrastructure for their lives. Then you step in. Over the last century, humans have turned up the volume in the ocean dramatically. Commercial shipping, with thousands of large vessels crossing the seas non-stop, injects constant low-frequency noise from engines and propellers. Military and industrial sonar adds repeated pulses at various frequencies and power levels. Seismic surveys and drilling operations contribute sharp, intense blasts used to probe subsurface geology. All of this stacks on top of the natural soundscape. To a whale, or a dolphin, or a fish that relies on hearing, this can sound like interference on a radio channel that used to be clear. Noise can mask communication signals, forcing animals to call louder, change frequency, or give up entirely. It can disrupt feeding if predators and prey cannot hear each other properly. In extreme cases, powerful sonar pulses or explosions can cause physical damage to hearing organs or trigger panic responses that lead to strandings. So the paradox is simple. The same physics that makes the ocean an excellent medium for communication also makes it an excellent medium for spreading your noise pollution everywhere. You don't have to be right next to a ship to be affected by it. You just have to share the same acoustic environment. But sound is not only about stressing animals, it's also your main tool for finding out what the ocean is doing when you're not there to see it. Networks of underwater microphones, called hydrophones, are deployed across the world's oceans. Some are old military arrays, some are research instruments, some are temporary deployments for specific projects. Together, they let you listen in on a wide range of events. These hydrophones pick up the calls of whales and dolphins, which is useful for tracking populations and migration routes. They also record the sounds of underwater volcanic eruptions, the rumble of seafloor earthquakes, and the crack and boom of icebergs claving and breaking apart. Even meteorites hitting the ocean's surface or exploding in the atmosphere can generate acoustic signals that carry through the water. And then there are sounds you still don't fully understand, the famous bloops, rumbles, and strange low-frequency events that have been recorded from time to time. Many of the well-known mysterious sounds have later turned out to be ice-related or linked to known geological processes. But some acoustic events are still not fully identified. They don't match any standard pattern you've cataloged yet. That doesn't automatically mean unknown monster. It usually means unknown process or insufficient data. But the key point is your listening network is still catching signals from an ocean that is more complex than your current models. Sound, in the end, is both your main window into the deep ocean and one of the main ways you are disturbing it. It reveals volcanic eruptions you would never see, ice movements in the polar night, and the presence of animals far from any ship. At the same time, your own noises are pushing against the limits of what those animals can tolerate. So the tension keeps building. You have an ocean that carries sound effortlessly, that lets life coordinate in a world without light, and that quietly broadcasts every major event across thousands of kilometers. And yet, below those sounds, there's another layer of mystery. Places where life is not following the normal rules at all. Places where sunlight is irrelevant and chemistry is enough to build entire ecosystems. If sound is the way you learn about the deep ocean, the next question is even more direct. What do you find when you follow those signals down to the hottest, darkest cracks on the seafloor, where water meets magma and life runs on chemicals instead of light? You grow up being told that life depends on sunlight, that plants capture light, animals eat plants, and everything else builds on that. But there are places on your own planet where sunlight does nothing and life still runs at full power. Down on the deep seafloor, in total darkness, you get whole ecosystems powered by rock and water reacting with each other, not by rays from the sun. How do you run an ecosystem where no light ever reaches, and the water is near freezing, and the pressure would crush you in a second? At hydrothermal vents, superheated, mineral-rich water blasts out of the seafloor at temperatures of 350 to 400 degrees Celsius, around 622 to 752 degrees Fahrenheit, while the deep ocean around it sits at just a few degrees above zero, a few degrees above freezing. The only reason that vent water is still liquid is the extremely high pressure. It keeps water from boiling the way it would at the surface. Inside that fluid is hydrogen sulfide, methane, and a cocktail of metals and other chemicals. Microbes there do something very simple and very radical. They use the chemical energy in those compounds to build organic matter in a process called chemosynthesis. Instead of using light to push electrons around, they use the energy stored in rock-derived chemicals. No photosynthesis, no sunlight, and yet you still get sugars, biomass, and full food webs. So if you have superheated water packed with metals and chemicals colliding with near-freezing deep-sea water, what kind of structure does that build on the seafloor? Does it just mix and vanish, or does it leave something behind you can see? When that hot, mineral-loaded vent fluid hits the cold seawater, many of the dissolved metals and sulfides instantly precipitate out. They turn into solid particles and grains. Over time, those particles stack and grow, forming chimneys and towers that can reach tens of meters, more than 30 feet, rising straight up from the seafloor. These are the so-called black smokers, named for the dark plumes of mineral-rich water they emit. The smoke is not gas, it's tiny mineral grains, mostly metal sulfides, blown out of the vent like a constant industrial exhaust. These chimneys are not static rock. They grow, collapse, rebuild, and move as the venting changes, and their surfaces provide hard, rough terrain for microbes and animals to cling to in an otherwise flat plain. But an ecosystem is more than hot water and mineral towers. So who actually lives there? What kind of animals can handle those conditions? High pressure, near freezing background, and jets of water hot enough to cook them if they get too close. One of the most famous residents is the Riftia tube worm. These worms can reach over 2 meters long, around 6.5 feet, and they live packed together around vents in dense clusters. They have no mouth, no stomach, no digestive tract in the usual sense. Instead, they live inside protective tubes and extend a bright red plume into the water. That plume is filled with special hemoglobin that can carry both oxygen and hydrogen sulfide at the same time, without letting the sulfide poison the worm. Inside the worm's body is an organ called the trophosome, packed with symbiotic bacteria. Those bacteria are the real digestive system. They use chemosynthesis to turn hydrogen sulfide and other chemicals into organic molecules, and the worm absorbs those molecules as food. In simple terms, the worm is a living apartment building for a bacterial factory. The animal moves fluids and provides structure. The microbes provide energy and nutrients. This pattern repeats around vents. Many animals host internal or external bacteria that do the chemistry, while the animals provide them with access to fluids and protection from the environment. So you might ask, is this kind of chemically powered life restricted only to places with extreme heat? Do you always need those 350 degrees Celsius jets? Or can you get the same trick running at normal deep sea temperatures? Cold seeps give you that answer. At places like the Haima cold seep, around 1,380 meters deep, roughly 4,500 feet, there is no superheated water. The surrounding ocean is still just a few degrees above freezing. What you do have is methane and hydrogen sulfide leaking slowly out of seafloor sediments. That leakage creates chemical gradients, and microbes can use those gradients as an energy source, just like at hot vents, but without the high temperature. Around these cold seeps, you find dense communities of clams, mussels, and other animals, many of them also filled with symbiotic bacteria that oxidize methane or sulfide. The animals do not graze on sunlight-powered plants. They act as containers and pumps for their microbial partners. In some cold seep areas, methane mixed with water forms solid methane hydrate in the sediments, a kind of ice-like solid that locks up large amounts of carbon. As that methane escapes and is consumed by microbes, a portion of it is prevented from reaching the atmosphere, but the system depends on a delicate balance between leakage, consumption, and physical disturbance. Again, you have an ecosystem that cares about chemistry first, temperature second, and sunlight not at all. So now the obvious question is, if you can run complex ecosystems in total darkness at high pressure, near freezing temperatures, using only rock-water chemistry, what does that say about where life can exist off Earth? For a long time, the default picture of habitable meant Earth-like planets with surface oceans under direct sunlight. But hydrothermal vents and cold seeps show that you can break the link between surface sunlight and life, as long as you have liquid water in contact with rock, plus some source of energy to drive chemical reactions. Look at icy moons like Europa around Jupiter or Enceladus around Saturn. Evidence from spacecraft suggests they have global subsurface oceans under thick ice shells, tens of kilometers of water with rocky seafloors below. Tidal forces from their giant parent planets flex their interiors, generating heat and probably driving hydrothermal activity on the seafloor. On Enceladus, plumes of water vapor and ice shoot out from cracks near the South Pole, and measurements of those plumes show salts and organic molecules that hint at ongoing water-rock reactions. On Europa, the surface is cracked and young, suggesting active exchange between surface ice and a deeper ocean. If hydrothermal vents and cold seeps on Earth can run entire ecosystems using only chemical gradients between hot or reduced fluids and cold, oxidized seawater, there is no fundamental reason the same playbook could not run on those moons. You do not need sunlight at the surface, you do not need continents or a thin atmosphere, you just need an ocean, rock, and energy. The discovery of chemosynthetic life at vents in the late 1970s rewrote the rules of habitability. Before that, many scientists assumed photosynthesis had to come first. Now you know that rock-powered life is possible and robust, at least here. That leads to a sharper question. If your own planet can hide entire alien-style ecosystems in places you never expected, powered by chemistry alone, what else is it hiding in the dark? And how do those organisms talk, hunt, warn each other, and coordinate in a world with no sunlight? The answer is a huge fraction of them make their own light, and the deep ocean, far from being black and empty, is full of controlled flashes, glows, and signals that you barely see from above. Down below 200 meters, the picture of a dark, empty ocean is just wrong. You're in a place where most animals probably glow, and the light isn't coming from the sun, it's coming from their bodies. In the midwater zones between the surface layers and the deep sea floor, estimates suggest that the majority of species, fish, squid, jellyfish, and plankton, can produce light through chemistry. So instead of thinking a few weird glowing fish, you should flip it. Bioluminescence is closer to the default down there, not the exception. The reason is simple. Once sunlight drops off, you either give up on vision or you build your own light sources. Many deep-sea animals go for the second option. They grow light organs called photophores, packed with cells or symbiotic bacteria that can emit controlled flashes or steady glows. Some species only have a few small spots under the eyes or along the sides. Others are covered in organized rows and patterns, almost like a coated panel built into the skin. This light isn't random, it's directed, tuned, and used for very specific jobs. So, how do you get living tissue to make light on demand without burning itself or wasting energy? The basic chemistry is usually a reaction between a molecule called luciferin, which actually emits the light, and an enzyme called luciferase, which controls the reaction, plus oxygen. When luciferin and oxygen interact, with luciferase speeding things up and shaping the process, energy is released, and that energy comes out as photons, as visible light. Cells keep luciferin in a ready state and then trigger the reaction when needed, a bit like opening a valve. Different species use different luciferins and different luciferases, and that lets them adjust the color and brightness of the light. Most marine bioluminescence is blue to blue-green because those wavelengths travel farthest in seawater. But some animals can produce greens, and a few, like certain deep-sea dragonfish, make red. Red light is interesting down there because many deep-sea animals can't see it. So a fish that produces red light and can detect it gets a private flashlight that doesn't announce itself to everyone else. That leads straight to function. If you can make light, what do you actually use it in a dark, dangerous environment? One big category is defense. Some shrimp and small crustaceans release glowing clouds of bioluminescent fluid when attacked, like an underwater flashbang or smoke grenade. A predator grabs them, they spit out a bright, expanding cloud, and in the confusion, they try to escape. In some cases, that glowing cloud can also make the predator more visible to even bigger hunters, turning the tables. Others use light offensively. Anglerfish, for example, have a modified fin ray on their head, a kind of fishing rod with a glowing lure at the tip. In the dark, small prey are drawn to the glow, approach to investigate, and get snapped up. In some cases, some squid flash bright patterns to stun or distract prey, buying a second to strike. In a world with limited visibility, any sharp contrast in light can grab attention and create a small window of opportunity. Then there is deception and camouflage. Hatchetfish are classic cases. They have photophores on their bellies that shine downward with a controlled brightness and color that roughly matches the light filtering down from above. Seen from below, their bodies blend into the faint glow of the surface, erasing their silhouette. This trick is called counter-illumination, and it's a direct response to the simple fact that many predators hunt by looking up for dark shapes against the lighter water above. Even within the same animal, different patterns and flashes can mean different things. Short, repeated pulses can be used to signal to mates or to coordinate schooling behavior. A steady, low glow can be for camouflage. A sudden, bright flash can be a startle response. This is why calling it glow in the dark is misleading. It's more like a coded light language, full of signals, warnings, and decoys. If you move back toward the surface at night, especially in coastal or productive regions, you see another side of this. Massive light shows driven by tiny organisms. Swarms of dinoflagellates, single-celled plankton can make entire wavefronts glow blue-green when disturbed. A boat wake, a swimming animal, or even your hand in the water can trigger millions of cells at once, each one releasing a tiny flash. 1 liter of seawater can hold millions of these microscopic pixels of light, and when they fire together, you get bright streaks and halos under every breaking wave. For the dinoflagellates, the light is probably a defense mechanism. When something big moves through their patch of water, they flash, which may attract larger predators to the thing that is eating them, or simply startle it. For you, it becomes a visible reminder that the ocean at night is not empty, it's densely populated, and many of its residents are wired with light. You might think humans would have picked up on all this a long time ago, but for most of scientific history, deep-sea expeditions were rare, short, and limited by crude technology. Early submersibles had bright white lights that scared many organisms away or washed out faint glows. Cameras were bulky, film was hard to use at depth, and windows were small. Observers saw the occasional glowing animal near the sub, but they did not get a full sense of how common bioluminescence really was. Only with modern, more sensitive cameras, low-light sensors, and quieter, more maneuverable submersibles and remotely operated vehicles did it become clear that below about 200 meters, bioluminescence is everywhere. Researchers who turn off the vehicle lights and let their eyes or instruments adjust describe seeing flashes, trails, and pulses constantly at all scales, from tiny plankton to large squid. In hindsight, humanity seriously underestimated how sophisticated light-based communication is below the sunlit zone. That late realization changes how you think about the ocean as a whole. You no longer have a simple split between light above, dark below. You have a layered system where sunlight controls life at the surface and self-produced light dominates much of the midwater. The ocean is full of signals you did not detect for most of your history because you were not looking with the right tools or with the right expectations. And that brings up a bigger issue because many of the organisms doing this glowing are the same ones that drive global cycles of carbon and oxygen. Once you admit that the deep and mid-water ocean are full of active, communicating life, you have to connect that to the air you breathe. The obvious next question is, if the ocean is this alive, this densely packed with plankton and other producers, how much of your oxygen budget, every breath you take, is actually being managed far out at sea by organisms you never see? You probably think your oxygen comes from forests and jungles, from the green stuff on land, but that's only half the story, at best. The other half is out at sea, in water you'll never touch, made by organisms you'll never see. Marine photosynthesizers, tiny phytoplankton, algae, and cyanobacteria produce at least half of Earth's oxygen, and some estimates push that up to around 50 to 80%. So when you take 2 breaths, odds are one of them is powered by the ocean. You don't walk through these forests, you sail over them or fly above them, and most days you don't think about them at all. These organisms work on the same basic principle as plants on land. They use light to convert carbon dioxide and water into organic matter and release oxygen as a byproduct. But because the ocean covers about 71% of the planet, and because light penetrates the upper layer of that water, the surface ocean becomes a gigantic, thin, photosynthetic film. The individual cells are tiny, but there are so many of them spread over such a huge area that their combined output turns into a major part of the planetary oxygen budget. So, if most of your oxygen is coming from microscopic life in the ocean, what does that forest actually look like? And how does it behave from day to day or season to season? Phytoplankton don't grow as trees. They grow as clouds. They form blooms, dense patches that can stretch for hundreds of kilometers, hundreds of miles across the sea surface. From above, satellites see those blooms as green, blue, or milky swirls. But standing on the water, you mostly just notice the color shift or a change in clarity. These are invisible forests, in the sense that they don't have trunks or leaves you can touch, but they pull carbon dioxide out of the atmosphere and pump oxygen back out, just the same. The scale is hard to grasp. A single liter of seawater can hold tens of thousands to millions of phytoplankton cells, all dividing, dying, and being eaten. When conditions are right, enough light, enough nutrients, stable water, these populations explode in size. They power food webs from the bottom up, feeding zooplankton, small fish, and everything above them. At the same time, they shift the gas balance between the ocean and the atmosphere, taking in CO2 when they grow and affecting how much CO2 the ocean absorbs or releases overall. That raises the next question. What happens to all that carbon once the plankton die or get eaten? Does it just bounce straight back into the air? Or can the ocean lock some of it away? When plankton die, or when animals eat them and excrete waste, some of that organic carbon forms particles that start to sink. These particles, mixed with bits of dead organisms, fecal pellets, and mineral dust, drift down as a slow, constant rain, sometimes called marine snow. Most of that material gets recycled on the way down, eaten again, decomposed, turned back into CO2 in the upper or mid depths. But a fraction makes it all the way into the deep ocean, below 1,000 meters, thousands of feet. Down there, water turns over very slowly. The carbon can stay locked in deep water masses or in seafloor sediments for hundreds to thousands of years. This whole process is known as the biological pump. It's one of the main reasons the deep ocean stores so much more carbon than the atmosphere does. You have a global conveyor moving carbon from the surface where it interacts with air to the deep where it is effectively parked on long timescales. So the ocean doesn't just make oxygen in the surface layer, it also hides carbon in the depths, moderating the speed and intensity of atmosphere changes. But that pump needs raw material, nutrients, to keep running. So where do those nutrients come from and how do they get back to the surface once they've sunk? Over time, as organic matter decomposes at depth, it releases nutrients like nitrates and phosphates into the deep water. Those nutrients are crucial for growth, but they're trapped deep down unless something brings the water back up. Upwelling zones are where that happens. In certain regions, winds push surface water away from coastlines or along the equator, and deeper water rises to replace it. That deep water is cold and nutrient-rich. When it reaches the sunlit layer, it can trigger huge phytoplankton blooms, because suddenly you have both light and fertilizer in the same place. These upwelling systems, off the west coast of continents like South America and Africa, and in parts of the Indian and Pacific Oceans, are some of the most productive marine regions on Earth. They support major fisheries, feeding millions of people, because the entire food web gets a boost from that nutrient injection. The traffic between surface and deep is constant, but not uniform. Some regions are strongly connected, with regular upwelling and vigorous mixing. Others are more stratified, with a stable layering that keeps surface and deep water separate. That structure is sensitive to temperature and wind patterns. You change those, you change the nutrient supply, and you change how much oxygen and carbon the surface ocean can handle. So what happens when you warm the ocean, add more CO2, and change its chemistry? Does this oxygen engine just keep running, or does it start to stall in ways that are easy to miss at first? Warming makes the surface layer lighter compared to the deeper, colder water. That increases stratification, meaning the layers mix less. Less mixing means fewer nutrients reaching the surface in many regions, which can reduce phytoplankton growth there, even if light is still available. At the same time, warmer water holds less dissolved oxygen, and metabolic rates of many organisms go up, making them consume oxygen faster. Acidification adds another layer of stress, as it affects some plankton species differently from others, potentially reshaping community structure. Some types may thrive in higher CO2 conditions, others may struggle. Changes in plankton communities can ripple upward through the food web and alter how efficiently the biological pump exports carbon to depth. In some areas, you also see expanding low oxygen zones, where respiration outpaces resupply, creating regions that are hostile to many higher animals. All of this means the ocean's role as an oxygen producer and carbon sink is not fixed. You are pushing on it by warming, by acidifying, and by changing circulation patterns. The changes show up slowly, over decades, and they're spread unevenly across basins, which makes it easy to downplay in daily life. But the underlying risk is simple. If the ocean's productivity and mixing patterns shift enough, the balance between oxygen production and consumption could change in ways that feed back on climate and ecosystems over long periods. So now you're looking at an ocean that not only shapes your climate, but also quietly maintains a big slice of the oxygen you rely on while you are warming, stratifying, and polluting it. That naturally leads to a harder question. If the water itself is structured, layered, and always moving, what about the currents inside it? The invisible rivers that move heat, salt, nutrients, and pollution around the globe? And what happens to your weather when those rivers start to change course? How do you talk about ocean currents in a way that really matches their scale? Because they're not small streams. They're more like whole moving continents of water that you never see on a map. Each major ocean basin hosts huge gyres, giant rotating systems thousands of kilometers across. In the North Pacific or North Atlantic, you're looking at loops of water that span entire basins, driven by winds, Earth rotation, and the shape of the continents. Inside those gyres, water, organisms, and floating debris can circulate for years. That's why you get things like the so-called garbage patches, areas where plastic and other trash slowly accumulate, not because there's a vacuum pulling them in, but because the circular flow makes it very hard for anything at the surface to leave. Inside a gyre, the surface currents move in big loops. The upper ocean slowly turns, and whatever floats gets caught. Plankton, fish larvae, drifting jellyfish all ride these invisible merry-go-rounds, some using them to spread, others getting trapped. For a drifting piece of plastic, this means a long sentence, spinning around in sunlit, nutrient-poor water, slowly breaking into microplastics. For the climate system, these gyres store heat and salt and keep them circulating on timescales of years to decades. So then you have to ask, if the middle of the gyres are these huge, slow rotating pools, where does the really fast action happen? Where does the ocean move like a jet instead of a gentle spin? Along the western edges of ocean basins, you get what are called western boundary currents, and this is where speed and volume go off the charts. Currents like the Gulf Stream in the North Atlantic or the Kuroshio in the North Pacific can flow at speeds over 2 meters per second, more than 4.5 miles per hour. That doesn't sound fast compared to a car, but for a mass of water tens to hundreds of kilometers wide and hundreds of meters deep, it is extreme. These currents move more water than all the rivers on Earth combined. You're talking about a liquid superhighway that transports heat and salt from the tropics toward higher latitudes. That transport is one of the main reasons places like Western Europe have milder climates than regions at similar latitudes on other continents. Warm water carried north releases heat into the atmosphere, changing air temperature, humidity, and storm development. If you change the strength or path of these jets, you change where winter storms track, how sea ice forms or melts, and how quickly coastal waters warm. But surface jets and gyring gyres are only the top story. Under the surface, especially along the equator, there are fast-flowing currents that most people never hear about because you can't see them from space. Along the equator in the Pacific and Atlantic, there are equatorial undercurrents, narrow, swift flows that run in the opposite direction to the surface currents above them. While winds push warm water one way at the surface, this undercurrent slides eastward at depth, carrying cooler, nutrient-rich water and rearranging heat below the surface. You would never guess these undercurrents exist just by looking at satellite maps of surface sea temperature or color, yet they are crucial. They feed upwelling in certain regions, they help set the temperature structure of the equatorial ocean, and they shape the background state for events like El Niño and La Niña. When they strengthen or weaken or shift depth, the timing and intensity of surface warming and cooling episodes can change. So now you have fast jets on the boundaries, undercurrents at the equator, and giant gyres in the middle. You might think that's the whole story, but the ocean adds another layer, swirling structures that look a lot like weather systems in the atmosphere. These are mesoscale eddies, rotating blobs of water, often tens to hundreds of kilometers wide, that spin off from major currents. Some rotate clockwise, some counterclockwise, depending on the hemisphere and the flow they detach from. Eddies can trap water masses for months to years, carrying their original temperature, salinity, and nutrient content with them as they drift. A warm eddy can bring tropical conditions into cooler regions, while a cold eddy can inject nutrient-rich water into otherwise poor surface areas, sparking localized productivity and attracting fish and larger predators. From above, satellites can see eddies as slight bumps or dips in sea surface height, or as patches of different temperature or color, moving like slow storms across the basins. These structures reshape marine ecosystems on regional scales. A single long-lived eddy can change where plankton bloom, where fish feed, and where top predators concentrate. Eddies also mix water vertically, stirring heat and carbon deeper or closer to the surface. If you leave eddies out of your models, you miss a lot of the actual day-to-day and month-to-month behavior of the real ocean. So once you understand that currents and eddies are constantly redistributing heat along the equator, up the western boundaries, and around the gyres, the next link is unavoidable. Your weather and extreme events are tied to this moving pattern. When currents misbehave, or rather when they shift in ways that push the system outside its usual range, your weather breaks in very visible ways. The El Niño Southern Oscillation, ENSO, is basically a coupled dance between Pacific trade winds, surface currents, and subsurface heat. In a normal state, trade winds blow from east to west across the tropical Pacific, piling warm surface water up in the western Pacific and allowing cooler, nutrient-rich water to upwell near South America. When those winds weaken, the warm pool shifts eastward, and the pattern of upwelling, currents, and surface temperatures reorganizes. That one shift in how the Pacific moves heat leads to floods in some regions, droughts in others, disrupted monsoons, and changes in hurricane or cyclone activity. The opposite phase, La Niña, intensifies the normal pattern, often bringing a different set of extremes. ENSO is a clear, recurring reminder that subtle changes in invisible ocean rivers can trigger very visible impacts on land, from crop failures to heat waves to infrastructure damage. Billions of people feel the effects, even if they never see a current or know which phase of ENSO they're living through at the moment. So put this together. You have swirling gyres trapping debris, boundary jets hauling heat poleward, hidden undercurrents steering equatorial balance, and eddies acting as mobile weather systems. All of that decides where the ocean is warm or cool, fertile or barren, calm or storm generating. And then you add the fact that you're heating the system, freshening parts of it with meltwater, and changing the winds that drive it. The internal plumbing of the ocean is already being pushed into new states. That sets up the next uncomfortable step. If these invisible rivers already control your climate and your extremes when they're in a relatively stable pattern, what happens when you start dumping your waste into them? Not just heat and CO2, but plastics, chemicals, and pollutants that ride the same currents, sink into the same depths, and show up even in the deepest trenches. The truth is, the ocean circulation is already carrying your fingerprints from the surface to the abyss, and the more you look, the more clearly you see them. When you picture the deep ocean, do you still think it is clean, untouched, somehow separate from human mess? Because the reality is the opposite. Your fingerprints are already stamped through almost every layer of it. One of the clearest markers is plastic, not just the bottles and nets you see in photos, but microplastics, fragments and fibers smaller than a grain of rice. Surveys now find these pieces from surface waters down into deep basins, and in some surface gyres, those big rotating systems you heard about earlier, densities can reach hundreds of thousands of particles per square kilometer. Any random patch of open ocean, far from land, can still be full of tiny plastic bits mixed into the upper water. These are not just floating there as neutral junk, they interact with everything around them. Microplastics can be colonized by bacteria, they can absorb other pollutants onto their surfaces, and they can be eaten by plankton, fish larvae, and filter feeders that mistake them for food. Once inside an animal, some particles pass through, some get stuck, and some leach additives and absorbed chemicals into tissues. Instead of being inert trash, microplastics become mobile platforms for extra contamination, hitching rides through the food web and across habitats. You might hope that at least the deep sea is safer, that gravity pulls most debris down and buries it somewhere out of sight. But the way it gets there makes the problem worse, not better. As microplastics stay in the water, they bump into organic material, bits of dead plankton, mucus, fecal pellets, and other particles. Over time, they clump together, and those clumps grow dense enough to sink. They become part of the marine snow, the slow rain of particles dropping from the surface into the twilight and midnight zones. That means synthetic polymers, materials that never existed in any previous era of Earth's history, are now being delivered straight into deep ecosystems that evolved with zero exposure to them. Animals that graze on or filter marine snow, from small zooplankton to deep-sea corals and sponges, are now exposed to a mixed diet of natural particles and plastic fragments. Sediments on the seafloor, which used to be built mainly from mineral grains and biological remains, now incorporate plastic fibers and shards as a routine ingredient. The very process the ocean uses to move carbon to the abyss is also moving your waste. So you have to ask, if microplastics and attached pollutants are writing the marine snow down, is there any place left that is genuinely untouched, or have you already reached even the deepest trench on the planet? Sampling from the Mariana Trench, near its deepest point, has found industrial pollutants like PCBs and plastic fibers in organisms and sediments at depths approaching 11,000 meters, about 36,000 feet. That is the same depth range as Challenger Deep, the extreme end of hydrostatic pressure on Earth. From the surface to the bottom of the deepest trench, traces of human activity are there. The deep trench fauna did not evolve with these compounds in their environment, yet you now find elevated levels of persistent organic pollutants in their tissues and plastic fragments in nearby sediments. Many of these chemicals break down slowly, so once they arrive, they stay for long timescales. The image of the deep sea as a pristine refuge is already outdated. The deepest point of your biosphere is now a sink for modern waste. Plastic is visible and easy to talk about, but it is only one category of what you are pouring into the ocean. A whole suite of chemicals ride rivers, sewage systems, and run off into coastal waters, and from there they spread outward with currents. Pharmaceuticals from human medicine pass through treatment plants and enter the sea. Pesticides and fertilizers from agriculture wash off fields and flow downstream. Heavy metals from industry, mining, and fossil fuel burning accumulate in sediments and water. These substances can bioaccumulate, which means they build up in organisms faster than they are broken down or excreted. Small amounts in plankton get concentrated as you move up the food web, from small fish to bigger fish to top predators like tuna, sharks, and marine mammals. By the time you're at the top, the concentrations can be many times higher than in the surrounding water. This is why health advisories sometimes warn people to limit consumption of specific fish species, especially large, long-lived predators. The ocean is not just moving your chemicals around, it is feeding them back into you through the things you eat. Now step back and think in terms of time, not just space. All of this plastic, all of these synthetic compounds do not just vanish. They settle into seafloor mud, layer by layer, year after year. Future geologists will be able to pull up sediment cores and see a sharp signal of your era. They will find a spike in microplastics, artificial radionuclides from nuclear tests and accidents, and industrial chemicals, all concentrated in a thin band of deposits. Above and below that band, sediments will look more natural, dominated by minerals and biological remains. In the middle, there will be a clear marker that a technological species was here. People talk about the Anthropocene, a proposed new epoch defined by human impact, and the ocean is where a big part of that marker is being written. You are engraving your present into the stratigraphy of the seafloor, not just with climate signals like changing shell chemistry and altered isotope ratios, but with direct, human-made trash and toxins. Long after coastlines have shifted and cities have eroded away, that chemical and plastic signature in the mud will still be there as evidence. So now you have a planet where the main climate engine, the main oxygen producer, and the deepest ecosystems are all being loaded with physical and chemical traces of your activity. And while all of that is settling and circulating, there is another force constantly reshaping the ocean in a quieter way, pulling entire basins up and down every day, moving your water, your heat, and your pollution back and forth with clock-like regularity. That force is not human at all. It is celestial. It is the gravitational pull of the moon and the sun, and it is literally lifting and dropping your oceans and slowly changing the spin of your planet. You drink a glass of water and it just sits there on the table, but the same water, when it's connected to the rest of the ocean, is constantly being pushed up and down by a rock in the sky and by the star you orbit. Tides are not a small coastal detail. They're proof that the moon and the sun are physically tugging on entire ocean basins every single day. The basic picture is simple. The moon's gravity pulls harder on the side of Earth that faces it and a bit less on the far side. and that difference creates tidal bulges in the ocean. As Earth rotates under those bulges, most coasts see two high tides and two low tides in roughly 24 hours. In many places, the vertical difference is just a couple of meters, maybe 1 to 3 meters, 3 to 10 feet. But in some narrow bays, it's over 10 meters, more than 30 feet. You are watching millions of cubic kilometers of water moving in response to gravity on a schedule that's tied to the moon's orbit, not to anything humans control. The sun adds its own pool, weaker than the moon's in terms of tides, but still important. When the sun, moon, and Earth line up during full and new moons, their tidal forces combine and you get spring tides, where the range between high and low is larger. When there are right angles, you get neap tides, with smaller ranges. So even the exact height of the water on your nearest beach is basically a graph of how the Earth-Moon-Sun system is lined up in space that day. If you're moving that much water up and down twice a day, the next question is obvious. How much energy is actually being pushed around, and where does it all go? Globally, the power being dissipated by tides is on the order of 3.5 terawatts. That's like running several thousand large power plants at once, but instead of feeding a grid, that energy is being lost as friction and turbulence in the ocean. When tidal currents race through narrow straits, around headlands, or across shallow continental shelves, they create strong flows, standing waves, and chaotic mixing. For local communities, you see this as fierce tidal races, currents that can hit several meters per second, dangerous for small boats, but also technically harvestable as tidal energy. For the planet, it means the tidal system is constantly converting gravitational energy into heat and mixing. That might sound small compared to the total energy from the sun, but in terms of stirring the deep ocean, that 3.5 terawatts really matters. So then you ask, is this stirring only at the surface and along coasts, or does the moon's pull reach all the way down into the stratified, layered interior of the ocean? When tidal flows move across underwater mountains, seamounts, and mid-ocean ridges, they generate internal tides. These are waves not on the surface, but along boundaries between layers of water with different densities. You can think of the ocean interior as stacked layers of slightly lighter and heavier water. When tidal currents shove those layers up and down as they cross rough topography, they create large internal waves that can travel hundreds of kilometers before they break. When these internal tides break, they mix water vertically, pulling colder, nutrient-rich water up and pushing warmer, oxygen-rich water down. They help erode the sharp density contrast that would otherwise lock surface and deep waters in separate worlds. So the moon is not just moving surface tides you can see, it is indirectly helping to ventilate the deep, and that feeds back into climate, ecosystems, and the long-term storage of heat and carbon. At the same time, the tide system has its own extreme events. Most days, tides are predictable and moderate, but when the geometry lines up in particular ways, the range can jump. When the moon is at perigee, its closest point to Earth, its gravitational pull is slightly stronger. If that perigee lines up with a full and new moon, so the sun and moon are pulling in the same line, you get larger than normal spring tides, often called king tides. During these events, even without a storm, high tide can push water higher up beaches, into low-lying streets, and against seawalls in ways that normally only happen during bad weather. Add long-term sea level rise on top of that, and suddenly king tides become tests of coastal defenses. Streets flood more often, groundwater in coastal aquifers gets pushed upward, and sewage or drainage systems back up. When a storm surge arrives on top of a king tide, the combined water level can be enough to overwhelm defenses that would have been fine under normal conditions. So the exact distance between Earth and Moon and the phase of the Moon are now factors in urban flooding risk. All of this motion, all of this friction raises one more question. If tides are constantly moving energy around and losing some of it as heat and turbulence, is anything else in the Earth-Moon system changing as a result? The answer is yes, on very long timescales. The tides are slowly breaking the planet. As tides slosh back and forth against coasts and seafloor, friction drags on the rotating Earth. That friction takes a tiny bit of rotational energy out of Earth's spin and transfers it to the Moon's orbit. The result is measurable. The Moon is drifting away from Earth at about 3.8 centimeters per year, around 1.5 inches per year. At the same time, Earth's rotation is gradually slowing, so the length of the day is increasing over geologic time. Hundreds of millions of years ago, a day was noticeably shorter, maybe 21 to 22 hours, with more days in a year. As time goes on, days will get longer, and the lunar distance will increase. The shape and depth of ocean basins will also change as plate tectonics rearranges continents, which means the exact pattern and strength of tides will keep evolving. So the tides you see today are one snapshot in a very long story where gravity from the moon and sun, the shape of ocean basins, and the roughness of the seafloor all interact. They lift and drop your coasts every day, mix your deep ocean, stress your infrastructure during king tides, and slowly rewrite the basic parameters of the Earth-Moon system like day length and orbital distance. Now stack that on everything else you've heard: extreme pressure, unmapped seafloors, hidden mountain chains, slow-motion climate machinery, and pollution reaching the deepest trenches. The environment that ocean life has had to adapt to is not just dark and cold, it's mechanically active, chemically shifting, and constantly stirred by forces from space. So the next question is, if you take a world like that and let evolution run for hundreds of millions of years, what kind of bodies, chemistries, and survival strategies do you get? And how far does biology push back against pressure, darkness, and hunger? How many of the biology rules you learn in school still hold when you drop life under hundreds of atmospheres of pressure into cold, dark water that barely gets any food? In the deep ocean, a lot of those rules get rewritten. Cells, bodies, even basic life cycles are reshaped to fit a world that would kill you in seconds. Start at the smallest scale, inside the cell. At high pressure, the problem is not just that your body would get squeezed, it's that proteins and membranes can change shape and stop working. Deep-sea organisms solve this by tweaking their chemistry. They load their cells with special small molecules called piezolites. These stabilize proteins and keep them from unfolding or clumping when pressure climbs into hundreds of atmospheres, even over 1,000 atmospheres in the deepest trenches. Some of these molecules also show up in shallow water species, but at much lower levels. In deep dwellers, the concentrations are high enough that if you took their biochemistry and put it in a surface animal, it would probably be toxic or at least disruptive. Down there, it's not optional, it's survival. Membranes need help too. If you just take a normal cell membrane and squeeze it hard and cool it down, it can get too rigid, like chilled fat. Deep-sea organisms adjust the kinds of fatty acids in their membranes, adding more unsaturated fats that stay flexible under pressure and cold. So at the molecular level, these animals are running customized hardware. Their enzymes, cell structures, and even DNA repair systems are tuned to a pressure and temperature regime that your own body would not tolerate for more than a moment. Then look at body size. In the deep sea, you get a strange mix of giantism and miniaturization. On the giant side, there are isopods, relatives of woodlice, that grow to the size of house cats. You get giant anthropods, oversized jellyfish, and large squid with long, trailing arms. One reason is that in cold, deep water, metabolic rates are slow, and bigger bodies can store more energy and glide efficiently. Large size can also help with moving long distances between scarce food patches. On the other extreme, you get tiny, stripped-down versions of animals that on land would be more balanced. One of the most extreme examples is the deep-sea anglerfish mating strategy. In some species, the female is the normal-sized fish with the lure and the teeth. The male is tiny. When a male finds a female, he bites and then effectively fuses with her body, connecting his blood supply to hers. Over time, he loses most of his organs and becomes a small, permanent sperm-producing appendage. In an environment where individuals are rare and widely spaced, this solves the "how do I find a mate at the right time" problem in a blunt way. You find one partner and you never let go. So you have pressure-tuned chemistry and extreme body strategies. Next, look at the actual physical design of many mid-water animals. A huge number of them are transparent and gelatinous. Instead of dense muscle and heavy skeletons, they're made mostly of water-rich gel, barely denser than the seawater around them. That has two big benefits. First, it makes them hard to see. In a low-light environment, being see-through is better than any color pattern you could paint on. Second, it saves energy on buoyancy. If your body is almost the same density as the surrounding water, you don't have to waste energy staying at a particular depth. You float, you drift, you make small adjustments. You see this in jellyfish, salps, many larval forms, and weird groups like ctenophores, the comb jellies. Some of these animals barely have any solid structure at all, just a thin layer of organized tissue wrapped around the mostly liquid interior. They're fragile, easily destroyed by nets, which is one reason science took so long to appreciate how common they are. Then there are the extreme specialists that show up when something big falls from the surface. When a whale dies and sinks, it becomes a whale fall, a sudden island of food on the seafloor. A whole succession of organisms arrives to use it. But one group is especially strange, the bone-eating worms called osedacs. These worms have no mouths and no stomachs in the usual sense. Instead, they grow root-like structures into the bone, and those roots release acid that dissolves the bone matrix. Inside those roots live symbiotic bacteria, which digest the released organic material. The worm, again, is basically a transport system and housing for microbes that do the actual breakdown. At a single whale skeleton, you can see dozens of osedac species, each occupying slightly different niches on the bone's surface. Without them and similar decomposers, large bones would linger much longer on the seafloor, and nutrients would be locked up instead of recycled into the deep ecosystem. All of this is happening in a place where food is scarce. Energy inputs to the deep sea are orders of magnitude lower than in surface ecosystems. No sunlight, no dense vegetation, just falling detritus, occasional carcasses, and chemosynthetic hotspots around vents and seeps. In that kind of environment, the winning strategy is usually go slow. Some deep-sea corals and sponges grow millimeter by millimeter, laying down skeletons and tissue at rates that feel almost frozen on human timescales. Dating work on some of these organisms suggests lifespans of centuries, and in a few cases, possibly over 1,000 years. A coral colony might start growing before a major human empire exists and still be alive long after that empire is gone. Sponges with tree-like forms can sit in near total darkness, filtering tiny particles from water that moves past them at a crawl. Their growth rings record changes in environmental conditions over time, like a living archive built into their bodies. Fish and invertebrates show similar patterns. Many deep-sea species mature late, produce fewer offspring, and live longer. That makes them extremely vulnerable to sudden human impacts. If you overfish a deep-sea species with that kind of life history, recovery can take decades to centuries, if it happens at all. You're not just tapping into a fast-growing resource. You're harvesting organisms that have been slowly building their populations under stable conditions for a very long time. So, taken together, deep ocean life rewires a lot of what you think is normal. It shows you proteins and membranes that are built for crushing pressures, life cycles that fuse animals together permanently, bodies that are mostly gel, worms that eat bone with acid and host internal factories of bacteria, and corals and sponges that treat centuries the way you treat decades. It's biology tuned to a planet that is dark, cold, and mechanically active most of the time. And here is the next step in the chain. All of these organisms live on and around the seafloor that is recording their existence grain by grain. Every shell fragment, every bit of organic matter, every chemical trace from your atmosphere and your industries is settling into layered mud that acts like a long-running tape recorder. If you want to know how this ocean planet has changed over tens of millions of years and how your own impact compares to past upheavals, you have to read that tape. The question is, what exactly is written there, and how clearly does it show that you're living in a new, human-driven chapter of Earth's history? How do you actually know what this ocean planet was doing 10 million years ago, or 50 million years ago, when there were no instruments, no satellites, no people at all? The answer is, the ocean has been writing everything down for you, quietly, at the bottom, in mud. Every year, a thin layer of particles settles onto the seafloor. Dust, volcanic ash, tiny shells, bits of organic matter, and chemical fallout from the atmosphere. Over tens of thousands, then millions of years, those layers build up into thick piles of sediment. When scientists drill down and pull up sediment cores, they're literally holding a vertical diary of the planet in their hands. You can see ash layers from big eruptions, shifts in color that match climate swings, and even fallout from past asteroid impacts. By reading those layers, you can reconstruct warm periods, ice ages, and extinction events that played out long before humans existed. The power of this record is in the detail. In a single core, a few centimeters of mud might represent 1,000 years, or even less. And that mud is full of microfossils, the remains of tiny organisms that lived at the surface, died, and sank. Their shells tell you who was living there, what the water chemistry was like, and with the right tools, how warm or cold the ocean surface was at the time. This is not guesswork, it's chemistry and statistics, repeated across many cores from different parts of the world, all cross-checked and dated. So the obvious question is, how do you turn a tiny shell into a thermometer? How do you look at a grain of calcium carbonate and say this was formed in water at a certain temperature? One of the main tools is oxygen isotopes. Oxygen comes in slightly different forms called isotopes, mainly oxygen-16 and oxygen-18. The ratio of these isotopes in seawater and in the shells that form from it shifts depending on temperature and on how much ice is locked up on land. Tiny shelled plankton called foraminifera, or forams, incorporate oxygen from seawater into their shells as they grow. When the water is warmer, they tend to build shells with a certain isotope balance. When it's cooler, the balance shifts. By measuring the oxygen isotope ratios in fossil forams from different layers in a core, scientists can reconstruct changes in ocean temperature and global ice volume through time. You stack those measurements layer by layer, and suddenly you have a temperature curve going back hundreds of thousands to millions of years. Combine records from different regions, and you get a global picture of past climates, including how fast they changed and how extreme they got. This is how we know, for example, that there have been past rapid warming events, but also that the current rate of change is unusually fast. The cores also show you when things went badly wrong for ocean life. In some layers, especially from certain periods in the distant past, the sediment suddenly turns very dark and rich in organic matter. These black shales are the fingerprints of ancient anoxic events, times when large regions of the ocean lost most of their oxygen. When deep waters no longer get enough oxygen, many animals die off, and organic material that would normally decay fully instead gets preserved. Over millions of years, with heat and pressure, those thick, organic-rich layers can turn into oil and gas deposits. So when you drill into a black shale, you're looking at the aftermath of massive stress in the ocean system, maybe driven by huge volcanic eruptions, rapid CO2 increases, or changes in circulation that cut off deep water ventilation. Marine life took heavy losses, ecosystems collapsed, and the chemistry of seawater shifted. These anoxic events are a warning written in rock that if you push the ocean too far, it can flip into a very different state, one that is bad news for many complex organisms. The ocean crust itself also records planetary behavior, not just in chemistry, but in magnetism. When lava erupts at mid-ocean ridges and cools, the iron-bearing minerals inside align with Earth's magnetic field, like tiny compass needles frozen in place. Earth's magnetic field sometimes reverses. The north and south magnetic poles swap. So as new crust forms, it locks in the current direction, and as spreading continues, you get stripes of normal and reversed polarity on either side of the ridge. When scientists first mapped these magnetic patterns on the seafloor, they saw symmetric bands of different polarity stretching away from ridges on both sides. That pattern was the crucial proof for seafloor spreading and plate tectonics. The ocean floor was not static, it was being created at ridges, moving outward, and then eventually being recycled at trenches. So even the solid parts of the ocean system are recording time. They show you how plates moved, how fast they spread, and when the magnetic field flipped. Now connect all of this to the present. Right now, melting ice sheets are adding fresh water to the ocean. Warming is shifting temperature profiles from the surface down, and acidification is changing carbonate chemistry. Every one of those changes is being recorded in the same sediment layers that captured past events. Shells forming today carry a different carbon isotope and trace metal signature than shells from 1,000 years ago. Microplastic grains and industrial chemicals are being buried alongside microfossils. Artificial radioactive nuclides from nuclear tests already sit in a clear layer in many cores, acting as timestamp markers for the mid-20th century. You are living in what many scientists argue is a new epoch, the Anthropocene, defined by human-driven changes to climate, chemistry, and biology. The ocean is writing that chapter right now. Future cores will show a sudden spike in certain greenhouse gas-related isotopes, a shift toward more acidic conditions recorded in shell structures, an increase in extinction and turnover rates of plankton species, and a sharp appearance of synthetic materials and pollutants that did not exist before industrialization. It will be a clear, thin band that says this is when one species started driving planetary scale changes. So the ocean is not just water and life. It is also your main archive, a time machine that lets you jump back to ancient greenhouse worlds, past ice ages and previous crises, and compare them to what you're doing today. And once you see that your actions are now part of that permanent record, etched in mud and rock alongside asteroid impacts and giant eruptions, the next question is unavoidable. Knowing all of this, and knowing how slowly the deep system responds, what do you actually do with the future ocean? Do you mine it, map it, protect it, or push it even harder than you already have? So now you're faced with a different kind of question. Not what is the ocean like, but what are you going to do with it? Because you're standing right at the moment when this whole hidden world is finally becoming reachable, and every new tool you build comes with a new way to damage it. For most of human history, the deep ocean was simply off limits. Too deep, too dark, too dangerous. That excuse is disappearing fast. New autonomous underwater vehicles, AUVs, and experimental robot subs are already going where you never will. Some of them weigh only a few kilograms, yet have reached depths close to 11,000 meters, around 36,000 feet, by using pressure-tolerant designs, oil-filled electronics, flexible housings, and buoyant materials that don't crush. Instead of building giant steel spheres, engineers are breaking systems into smaller modules that can survive pressure by bending with it rather than fighting it. That means more dives, more data, more footage, and also more ability to stay down for weeks or months without a human on board. So the old barrier, we can't get there, is fading fast, and that forces a blunt question. Once you can get to the deepest few percent of the planet cheaply and often, do you treat it as a lab, a mine, a dump, or a protected zone? Right now, interest in seafloor mining is rising fast. On the abyssal plains, between about 4,000 and 6,000 meters deep, you have fields of polymetallic nodules, potato-sized lumps rich in manganese, nickel, cobalt, and rare metals. On mid-ocean ridges and in some back arc basins, you have seafloor massive sulfide deposits around old hydrothermal vent sites, loaded with copper, zinc, gold, and other metals. These look, on paper, like tempting sources for the materials you want for batteries, electronics, and renewable energy infrastructure. The argument you hear is simple. We need these metals, let's pick them up. But the ecosystem sitting on and around those deposits took millions of years to form. Nodules grow at rates of millimeters per million years. Many animals use them as hard substrate in an otherwise soft, muddy landscape. Vent and post-vent communities assemble around steep chemical gradients that are fragile and poorly understood. Your sampling, so far, has barely scratched the surface of how these systems work, how long they take to recover, or if they recover at all after heavy disturbance. You're dragging heavy machines across nodule fields don't just remove rocks, you erase habitats that took geologic time to appear. The paradox is that you're talking about mining the planet's life support system, the same ocean that stabilizes your climate and feeds billions, for short-term material gains. Then there's the deeper timescale, because whatever you decide about mining is happening on top of another process you can't turn off, the slow adjustment of the deep ocean to your emissions. The choices you make about greenhouse gases, pollution, and conservation over the next few decades will set trajectories that extend into centuries and millennia. When extra heat and CO2 enter the ocean, they don't just skim the surface, they gradually mix downward, changing temperature and chemistry in water masses that may not see the surface again for hundreds of years. Deep water formation near the poles, changes in stratification, and altered currents will reshape how the deep ocean stores heat and carbon. So a decision made in a policy meeting this decade can affect the temperature and acidity of deep waters in the year 2500. You're effectively turning knobs on a machine with a huge time delay. By the time the deep response is fully visible, many generations will have already lived and died with the early consequences. That's what deep climate leverage really means. The ocean will eventually reflect what you do now, and it will hold that signal for a very long time. At the same time, you're still working with a very incomplete map. Only about a quarter of the seafloor has been mapped in detail with modern sonar, and more than 99% of the deep seafloor has never been seen directly by cameras. You've been making global-scale decisions about climate, fishing, and possible mining, while most of the terrain and most of the ecosystems are blank on your mental map. The odds that there are unknown habitats, mineral structures, and even basic physical phenomena still hiding down there are high. Entire types of vents, new chemical systems, and unfamiliar forms of life could be sitting a few hundred meters from where a survey line once passed, completely missed. That uncertainty cuts both ways. On one hand, it's exciting because every new deep mission has a real chance to find something nobody expected. On the other hand, it means any large-scale disturbance, from trawling to mining to waste dumping, risks wiping out things you haven't even discovered yet. You're operating in the last major physical frontier on Earth with tools finally good enough to see detail, but with economic pressures already pushing to exploit before you fully understand. So here's the twist you can't dodge. The alien world you keep looking for with telescopes and space probes already surrounds you, right here in saltwater. You want extreme pressures? They're under your ships. You want life that runs on chemistry instead of sunlight? It's on your own seafloor. You want strange ecosystems, slow-motion climates, and long-term archives of planetary history? All of that lives in the ocean. The ocean is not background scenery in the story of Earth, it is the main character. Land, atmosphere, ice, and human civilization are all side plots that only make sense once you understand what this water planet is doing. You are just now learning how to read its script, with robots reaching the trenches, satellites tracking currents, and cores pulling up its memory. At the same time, you are editing that script in real time with CO2, heat, plastics, and noise, whether you admit it or not. The deep ocean will remember what you do next, in chemistry, in sediments, in which species survive, and in how currents and climate settle into new patterns. So the real decision in front of you is simple and hard at the same time. Do you treat this ocean as an expendable resource, or as the central system that keeps your world livable? Do you act as if you live on a land planet with some water on it, or as if you truly understand that you're a land-dwelling guest on a water planet that can get along fine without you? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.